The introduction of dual-arm robots in human-based assembly lines will eventually increase the automation level, enabling the human to work on value-added tasks and to reduce physical stress of the operators. In this direction, the adoption of dual-arm robots seems promising, as it allows for multitasking as well as space and cost efficiency by simplifying fixtures and gripping devices utilizing both arms for manipulation. The dual gripper concept has been integrated into an industrial dual-arm robot, allowing the handling of big and heavy parts along with the smaller ones without requiring the changing of tools. These parts are not so heavy for robots, rather they are heavy for the human. Without changing grippers, the robot was used to manipulate both a traverse weighing 12 kilos and the fuse box weighing 500 grams, using a traditional push and start screwdriver, which can also be used by a human. The dual-arm robot was able to fasten screws on the fuse box with the same grippers. There are still tasks that should be carried out by the human, such as the installation of a wire harness on the traverse of a vehicle dashboard. The human robot station controller allows the execution of both human and robot tasks in a safe way. The user is able to signal the start and the end of a human task via gestures, voice commands, or buttons on the user-friendly graphical interfaces. In order for humans and robots to achieve a close coexistence, advanced and certified safety solutions are required. A high-level task description has been programmed in order to be easily monitored by a non-expert user. Intuitive human-machine interfaces have been developed, enabling the programming time reduction. In this direction, the user is able to move the robot by using external software tools. The human can also move the dual-arm robot with simple body and hand gestures, as well as graphical interfaces. The cooperation of both arms is possible in this mode as well. The robot's speed is adjusted at a low level, following the same logic as that of the traditional programming approaches. Motion planning algorithms in combination with depth data have been also evaluated for the collision avoidance application. The user selects the target position in a simulation environment and a collision-free path is generated. The path is virtually generated before sending to the robot for execution. LMS has also worked on the development of applications for dual-arm concurrent motion planning. A multi-criteria decision-making framework was used in order to allow the generation of dual-arm motion paths in the configuration space. The use of an alternative offline programming approach was proposed, enabling the dual-arm robot to mimic human motions. The human data were captured in a virtual reality environment and were further processed and sent to the robot for execution. In this way, the programming time is significantly reduced while accuracy issues still need to be improved. The simulation of cables and wire harnesses was also investigated through the evaluation of different simulation platforms and physics engines. LMS has developed a new physics engine along with testing the existing ones.